Okay, everybody, welcome to discussion 7. This week I talked a little bit about on Monday about lab 3, which was probably a little more pertinent info for the Monday people. Now everyone's at least started lab 3, but I'm going to go over the same material just because I think it's helpful if you haven't seen it, and it might help you with lab 3 if you're still working on it. On that note, I guess I'll just say that lab 3 we just announced will not be due at the start of your lab section next week. It'll be due 24 hours after that. So if you have lab next Monday, the 19th, it'll be due Tuesday at 5 p.m. And then if you have lab on Tuesday, it'll be due Wednesday, the 21st at 11 a.m. Okay, so that should give you time to come to lab section and get your questions about lab 3 answered, and then hopefully give you a chance to finish things up and get the report in. It'll be in your best interest to get as much done as possible so you can spend some of this lab time working on pre-lab 4, which will be due the following week at the normal time, so at the start of your lab section on the 26th and 27th. Okay. Homework 7 is online and due on Friday. I'm going to talk a little bit about one of those problems that I think probably will be difficult without some help. So that's the plan for today. Yeah, I'm going to introduce LT-SPICE, which is another alternative to H-SPICE, which we've been using so far. And we'll see the differences as we get into this. So if you were in lecture today, Professor Nguyen has stressed that one of the most important things you'll take away from this class is the concept of small signal analysis, and that it's applicable not only to analog circuits, but to a myriad of other things. Many electromechanical systems that we deal with in our research use this idea of a bias point and small signal excitations about the bias point to get a linearized kind of version of a transfer function. And so the bias point, let's just talk about a couple definitions. The bias point, when we talk about it, we sometimes refer to it as the operating point or the Q point. It's kind of, you can think of it for a specific circuit, it's the set of all the DC node voltages and branch currents. So imagine, someone gave you a circuit and they asked you to figure out what its DC operating point is. Well, to be thorough, you would basically find all of the currents in every single branch and all the voltages at every node. And that's the DC operating point. Now, oftentimes we don't care about every aspect of the DC operating point. There's specific currents and specific voltages that really are going to affect our performance. But generally speaking, that all of that information comprises the DC operating point. And so small signal analysis assumes that we choose an operating point and then that our inputs, that are centered about that operating point do not deviate very far from that operating point. So basically they operate within close proximity to that bias point. And so with circuits, the idea of operating point is often just a DC voltage, and then a small signal is an AC voltage with a small amplitude. Okay, and so that small magnitude of excitation in the input, so that small AC amplitude, will cause a fluctuation in the output that will be a different size usually. And the size of that output fluctuation, is proportional to the slope. In this case, our example is an IV characteristic. And a lot of times we will talk about IV characteristics because for transistors, it's a very useful way to look at a voltage controlled device, where the drain current is the kind of parameter that we're controlling. So we plot the drain current versus the control voltage or something like that. And so in this case where we have I on the y-axis and V on the x-axis, the slope of that IV characteristic kind of tells us, well, how big will our output fluctuation be for a certain input fluctuation? And so the math of it, Professor Nguyen went over in a lecture today, it involves Taylor series expansion of your function about that bias point or that operating point. But it really, you can think about it qualitatively as well. And you can just think about it's the idea where if you take a tangent line to your curve at a certain operating point, and you take the slope of that tangent line, then as long as you don't move very far from that operating point, you can assume the slope doesn't change too much. And if it's a small enough deviation, we can just assume the slope doesn't change at all. So in that case, we have a linear function, and that means that's predicated on the assumption that we are staying close to that operating point. And so here we have, three different examples of different bias points and how the kind of bias point affects the small signal properties of this IV characteristic, right? And so in small signal, we care about the slope at that bias point. So say, take the first, point here, the blue dot, that operating point is at a point where the slope is very steep. And remember, this is an IV characteristic. If it was a V versus I characteristic, a large slope would indicate a large resistance. But because we have the two flipped, that basically means that a large slope means a very small resistance or a large conductance. Okay, and so we're defining resistance as a change in voltage divided by a change in current, kind of its most basic definition. And so if we have a very steep slope at our operating point, that means we're going to have a very small RDS. Now, if we look at another case where we have a much shallower slope, but there's still a non-zero slope there, well, that's going to indicate a large RDS, right? In this case, RDS is the drain to source resistance, but really this is kind of just generally speaking a resistance you could define based off of this IV characteristic. Because an ID, the drain source IV characteristic isn't really going to look like this ever. So those are two kind of finite values of the small signal resistance. And then if you look at a point where the slope is actually 0, well, if the slope is 1 over the resistance, then that means you have basically infinite resistance at that point. And so depending on where we are on our IV characteristic, we will have different values for small signal resistance, where small signal resistance is basically, what does the resistance look like for a signal that's just operating in this region? Okay. Any questions about this? So this is a really important concept. It's okay if it's not, immediately clear to you the implications of this. You might understand what I'm talking about, but it doesn't fit into the context of circuit design, but it will eventually. And so just, come back to this basic understanding of the small signal analysis if you ever are confused. All right. And so for pre-lab 3, I'm going to go through this a little bit quickly just because most people have already finished the pre-lab, hopefully, and are well into lab 3. Didn't mean to cover that up, so I'm just actually going to move over to this next slide because it has all the same information. So we're dealing with MOSFETs, and we're dealing with them in the linear region of operation. And so in the linear region of operation, we have an expression for the drain current. IDS is mu n the mobility times Cox, which is technically it's the gate capacitance. Yeah, that's the gate capacitance. And basically that includes the W over L, right? This is Cox double prime times W over L. And multiplied by the VGS, the gate to source voltage, minus the threshold voltage. That voltage difference we call the overdrive voltage because it's how far over the turn-on voltage we are driving this transistor. And then we see that we are actually quadratic in VDS. So we have a squared term for VDS indicating there is a nonlinearity present in this curve. And that's even before we get to the saturation region, right? We're going to see some curvature of our MOSFET IV characteristic. Now, again, we go back to our definition of small signal resistance. It's the change in a voltage divided by the incremental change in a current. And so basically DI, DS, dVDS, we take 1 over the derivative of our RDS with respect to VDS, and that gives us our small signal resistance. Okay. And so for small values of VDS, kind of make this assumption. You can either, assume that VDS is small and VDS squared will be even smaller and just set this to 0, or you could actually go through and leave that VDS squared term intact when you take the derivative of IDS with respect to VDS, and you'll get, something that's a small signal resistance that still depends on VDS. And so this is not really our linear function that we're looking for quite yet, because it's still depending on your drain to source resistance, sorry, drain to source voltage. And so if we had a constant small signal resistance, that would be what we're looking for. But really the thing to take away from this is that it's not just important that VDS is small, it's really about what VDS is small relative to. And so we want VDS to be small relative to the overdrive voltage. Basically, VDS can't get too close to our VGS. If it gets within a threshold voltage, we're going to go into saturation. And the further we are away from that saturation point, the more linear our current equation will look. And so okay, hopefully you didn't lose me, my audio, but I think software cut out for a second there. So like I was saying, we want VDS to be much smaller compared to VOV to see a linear relationship between I and V. And so in that linear region, we're going to kind of assume that we're going to keep VDS small relative to VOV. And we get something that looks like 1 over mu n Cox times VOV. Right? So this equation is constant with respect to VDS. So we basically have a number for our small signal resistance based off of a given VOV. And so now we have our voltage controlled resistor. And the whole takeaway is that we've gotten a value that's independent of our port voltage current. In this case, our ports are our drain and our source. We're kind of using those as our input and output to the device. And so we've basically linearized our IV characteristic about that bias point. So plotting the IV characteristic in SPICE, so this is specifically, right, this is going to be IDS or ID. Sometimes IDS will refer to the, so I'll usually try and just use ID to talk about the drain current. So this is ID versus VDS, right? And these are increasing values of VG, so VGS. So VGS increasing, right? So the uppermost curve is for the highest VGS and the lower curve is for the lowest VGS. All right, so if we zoom in on this region where VDS is much smaller than VOV, then all of a sudden this IV characteristic does actually look linear. And so you can kind of get an intuitive understanding of the linearization by just zooming in, right? Because if I zoom in, that's basically implying that my signal isn't going to leave a very small area or very small region of the curve. And so if we take a little bit wider of a window and we actually look at VDSs that are approaching VOV, right? We're no longer going to see things are as linear. And what we see is that the larger our VGS is, right, the more linear our ID VDS characteristic is. And that kind of confirms what I was saying earlier about VDS must be small compared to VOV. And so as VOV gets bigger, I get basically a wider range of VDS that looks linear. And so for these, very small VOV values here, which I'm using VOV as a kind of a proxy for VGS, but for small values of VGS, we see that the curve really isn't linear at all. It starts out with basically its largest value of its slope, and then it rolls off into basically a flat line. And so for a larger overdrive voltage, you get better linearity of your RDS. So this is the first circuit you will build if you haven't built it already. And after you've basically characterized your transistors, taking the curves, basically measuring the curves we kind of just looked at simulations of. And when you did the pre-lab, hopefully you were able to kind of just take this transistor, analyze it based off of its ideal kind of drain source configuration in a given VC, and then find an equivalent resistance to substitute for this transistor. And so basically we're taking a 4-terminal device and we're turning it into a 2-terminal device based off of VC and VB. And we're going to assume that it stays in the linear region. And if we do that, then we can basically just take a very basic equation for our gain, which is just the RDS of our transistor M1 divided by R1, right? And so in this case, RDS is basically going to be equal to 1 over mu n Cox double prime W over L times VGS minus VTH, right? And we call this K, N, and this can be our VOV. And so we could think of this as just a drop-in substitute for the transistors. We just have this resistor with value RDS. And we know that, hopefully you took into account the back bias or the body bias here. So VSB not equal to 0. So we have a non-zero kind of source to body voltage, which means that the body effect is something you need to take into account. The body effect will just basically modify your effective threshold voltage. If your threshold voltage is modified, then that means your VOV here, effective VOV, is going to be different. Okay, this should all be kind of review for you, but feel free to stop me if anything doesn't quite add up for you. And so here is the second circuit. It's what we call a bandwidth controlled filter. In this case, it's really like a low pass filter, right? And the bandwidth is basically 0 hertz to our cutoff frequency. And past that cutoff frequency, our filter is going to kind of roll off to the point where we aren't going to see any signals passing through it. And so this is a unity gain buffer in the sense that these two transistors are ostensibly pretty well matched. They're in the same package. They're probably on the same piece of silicon and they're in the same substrate, right? So they've gone through the same processes. There will be some slight variations, but for the most part, we can assume they're pretty well matched. What does that mean? Well, if we're taking the small signal resistance of these two transistors, again, kind of assuming that they stay in the linear region, right? We're going to assume that we can keep the drain and source voltages such that these transistors never really leave the linear region. We'll see how good of an assumption that is when we actually build the circuit. But for now, to understand this at an intuitive level, it's best to just kind of assume the simplest scenario. So in that case, right, we have basically two impedances that stem from these transistors in the linear region. So we have the impedance of M1, which we'll just call Z1. And then we have the impedance of M2, which we'll call Z2, which is in parallel with this capacitor C2. And then those impedances are put in an otherwise standard looking inverting configuration where we have our reference, kind of our non-inverting terminal is grounded, and then we have feedback, negative feedback. And so in this case, actually to make this even more general, let's call this R1, and we'll just say that's equal to Z1. And then this is R2. But let's take this entire parallel combination of R2 and C2 and call this Z2. Then we can very easily write the expression based on our knowledge of an inverting amplifier that the gain from input to output is negative Z2 over Z1, where Z2 is the impedance in feedback and Z1 is the impedance in series with the input. So hopefully you can kind of see how this matches the case we are normally used to. And so kind of done the math down here. Hopefully you did that in your pre-lab, but basically you get that C2 creates a pull along with the resistance across it. So you get a pull at R2, C2, and that pull is going to change depending on the value of R2. C2 is staying constant, but because we're changing the resistance across the capacitance, the effective pull frequency is going to change. Okay, and so that's how we adjust the bandwidth of this circuit. Now, when we get into the lab, and you've probably already learned this, so I'm not going to spend too much time, but we realize that these circuits are, not necessarily just a 4-terminal device that's clearly labeled gate, drain, source, and body, right? We actually have to look at our schematic and our data sheet and figure out which pin corresponds to which terminal of the device. And so hopefully when you were characterizing your transistors, you realized that you have to find devices that have separate access to their body and their source terminals. And so this is a better version of the drawing that's in your data sheet, but that little dot right there indicates that VB1 is equal to VS1, right? The source of M1 is shorted to the body of M1. So there's not going to be a VSB. Basically, we can say that VSB1 is always equal to 0. Well, for this lab, we want to see the effects of a body bias, right? We want to see that body effect on our threshold voltage. And so you should really be using only M3 and M5, because those two transistors allow you to apply a body bias here, VB, and it's going to be VB1, VB2, and VB3, right? It's connected to the body of all three. And then VS3 and VS5 are separate from that body terminal. So yeah, let me fix this. VB1, 3, and 5, because those correspond to M1, M3, and M5. So don't use the PMOS. Don't use this pin, which actually this pin is labeled VDD, which is kind of misleading. We don't need to supply power like we do to an amplifier. So don't connect anything to that VDD pin. Make sure there's nothing floating, even like hanging off of it, because it can change things. Yeah, I think that's all I have to say about the package. And then when we actually test these circuits, hopefully this, if you've started this, this is kind of clear to you, but if not, that's totally fine. We want to make sure that our assumption that we keep these MOSFETs in the linear region holds true. And really the main thing to do is to ensure that the MOSFET never goes into saturation. And so to stay in the linear region, we have basically one condition. As long as our transistor has a VGS above cutoff, then I should say we have one condition as long as VGS stays above cutoff, then that condition is that our drain to source voltage is less than that overdrive voltage, VGS minus VTH, right? And so really our drain to source voltage is just VD minus VS. We want to make sure that's less than VG minus VS minus VTH. And what we get is that VDG has to be less than negative VTH. In other words, we can flip these signs and say that VGD has to be greater than VTH. So our gate voltage has to be at least VTH above our drain voltage. And the reason I wrote this out this way is because this kind of tells us that we don't care really about the source voltage. All we care about is the relationship between the drain and the gate voltage. So another way to look at it is that VD is always less than that VG minus VTH. And so when we look at this circuit, let me draw the rails here. We have plus 5 volts and minus 5 volts power supplies. And so we know that if we center our input around 0 volts, our VI will be positive and negative, and our VO will be positive and negative, right? It'll oscillate, both output and input will oscillate about those bias points, which are going to be around 0 volts. Well, the problem then becomes VC is always positive. And so if V out ever gets more positive than VC, what we really have when we talk about VD and VG is that V out, which is VD, has to be less than VC minus VTH. So if that V out gets too big, then we are going to put this transistor into the saturation region. Remember the curve, the basic shape looks like this. So if we're in the saturation region, the slope di dV is very small. Remember, our small signal resistance is 1 over that slope. So we're going to have a really large small signal resistance. And basically at that point, you're going to get a huge increase in gain, maybe even approaching the open loop gain. If this slope is small enough, right, and then we'll have infinite resistance. And your signal might look like this, where it looks okay on the downswing, and then it shoots up, hits the rail, and then it comes back down, and it follows the input, and then it shoots up, direct like a delta function, and hits the rail straight up, right? And this just indicates that you have some nonlinearity and that your gain is changing at different points in the cycle, right? You want your gain to kind of stay constant. And so one way to do this, kind of a simple way to do that, is to just bring both the input and output very negative, so that VC is always going to be more positive than the output, right? Because what we care about is that VO is less than VC minus VTH. Well, if you think about it, if we've been kind of hammering home the idea that these transistors are actually symmetrical, right? So the drain and the source are almost interchangeable. It's really just whichever terminals at the lower potential, that terminal will be considered the source. And so I really should say that V minus or VO, depending on where we are in the cycle, has to be less than VC minus VTH. And so what we do is instead of grounding our non-inverting terminal, we set a bias point that's negative. And then we set that same negative bias as our input bias. And so our input signal looks something like this. If this is V in, I'll say that's the total V in, so I'll do lowercase v capital IN, and this is time. I'll say this is 0 volts here, and then we're going to apply a negative DC voltage, VI, where VI is less than 0, and then I should say capital V capital I, and then we're going to have a small AC excitation with amplitude VI about that negative bias point. And the idea here is that VC is somewhere up here, right? VC is some positive voltage that's staying constant. And so we want to make sure, that our VI and our V out stay below that VC. And, V out might even be something like this, where we have a bigger signal. Well, let's get this right. So we're going to have a 180-degree phase shift, right? And we're going to have gain. So something like that. But again, we've brought the bias point so low that our V out has a negative voltage at DC. And that negative voltage just tells us that V out will be centered about a negative voltage. And as long as it never gets too big relative to VC, we're okay. And so you can play around with the offset of VI, right? This capital V, capital I. This is the offset in your wave gen. It's like the DC value of your signal. And you can play around with that and see that as you bring that closer then to 0, then VO will actually get close enough to VC where you'll hit saturation and your gain will jump up. And so to do that, we basically generate V bias just by using a voltage divider. So this V bias here should just be connected directly here, right? I'm just modeling V bias as a voltage source, but really this should just be connected to a voltage divider. So if this is our negative, let's just say our negative 5 volts is here. Right, that's going to connect to the negative rail of our op amp, and then we're going to take divided version of that and send that to V bias. Okay, so we're basically, I would have you just use another voltage source on your bench if you were in the physical labs, but since we don't have that luxury, we're just using a voltage divider to create another voltage source. And that voltage source, it's okay to use a voltage divider because the input impedance of our op amp at the non-inverting terminal is so large that even though there's some output impedance to this voltage source, right, it's not ideal. RS is not 0 for V bias. that's okay because our Rn is so large. Okay, that's all I have to say about lab 3. Of course, that took longer than I expected, but I want to go through LT-SPICE kind of quickly. How come VO won't be inverted? So VO will be inverted, but are you talking about the DC value of VO? So the DC value of VO, if you just do the analysis, you'll basically see, so say VI is very negative, right? My capital V, capital I. Then I'm basically have the same, if I set VI equal to V bias, which is what you want to do, it says this in the lab, you'll set VI equal to that V bias value. Then this should also kind of be V bias here. And so we basically have no current going through this, this resistor, although there will be a little bit of offset that might make there some current. And that essentially means that if there's no current flowing through that resistor, then there's not going to be any current flowing through this transistor. If there's no current flowing through the transistor, then that means that VO will kind of be at the same voltage as V minus here, right? Because there's no current flowing through it, there's no voltage drop. And so that means kind of VDS is 0. Well, if VS is V bias, that means VO is approximately V bias. And again, V bias is negative. And so you'll see that your output DC value is going to be negative for an input that's negative. Okay. Okay.
Can I ask one more question about that?
Sure.
So if you had like a positive VI, like a positive DC VI and sorry, no. So you have a negative DC bias VI and then like some AC signal on top of that, right? Yeah. So if you invert that, then the VI would become a positive DC signal, right? And then the AC signal would just get phase shifted by 180. So in that case, why wouldn't you be in danger of like your total signal being more than VC minus VTH?
So the inversion, because of this MOSFET, is not going to occur at DC. And so the bias point of the output will not be an inverted, basically, version of the input DC. And so you'll get you'll definitely get a 180-degree phase shifted signal about that DC output voltage, and it'll have a larger amplitude than VI. But really what you'll see is that it's still going to be, as long as you can keep that bias voltage at the output low enough, then V out will stay negative even on the upswing.
Oh, okay. Got it.
Yeah, and we can talk more about this in office hours too. I want to get to LT-SPICE just while I have everyone here. And so LT-SPICE is basically a GUI version of H-SPICE, where you can drag and drop and double click on something and edit the value of it and stuff like that. So you're basically, you're controlling the generation of a netlist through a graphical interface. It was developed by Linear Technology, who was acquired by Analog Devices a few years back, and it's completely free. You can go to www.analog.com, and I think 17 is still the latest version. You should be able to get it for Windows and Mac, I think Linux as well. And so when you first open LT-SPICE, you're going to see a window like this. And at this point, I'm going to switch over, and I think I'm going to basically run through the tutorial in real time, and the slides will show the tutorial for reference later, okay? So I'm going to share this. Can everyone see the LT-SPICE screen I'm sharing now? Or are you still seeing the slides? Okay. Can you confirm now that you see the LT-SPICE screen?
Yeah.
Great. Okay. So this is what you'll get. It looks kind of like a gross coffee stain. the first thing you'll want to do is just create a new schematic. You can click this button here. You can go File, New Schematic. And then to place components, what you'll do is, let me move this zoom overlay. So along the top of the toolbar here, you'll see actually just visual representations of different components. So you can click this resistor, and then you can place a resistor. You can scroll down to zoom in and scroll up to zoom out. You can place that resistor, and then it'll automatically increment the values of these, or I shouldn't say the values, the names of these resistors, the labels. I can go hit escape and I'll get out of resistor mode. I can place capacitors, things like that. And so there are also hotkeys. I can hit R and go into resistor placement mode, C. I can hit L, right? There's different ways to trigger these commands. You can play around and see what's comfortable with, most comfortable to you. And if you're inserting something that's not a resistor, capacitor, inductor, or diode, you can use this component. It's a little AND gate. This component symbol will open up the library. This is just the default library that comes with LTSpice. And so for things like a voltage source, you go to voltage. You should see that you can make a DC, AC, pulse, sine, all these different types of voltage sources. You can click OK, and then you'll be in voltage source placement mode. And again, you'll be in this mode until you hit escape. Okay. Once you place a component, you right click on it and to edit the values. And so for this voltage source right now, which is a basic DC source, I could add a DC value. I can add a series of resistance. That's it. Or I can go to advanced and change the source to a different type. So I can do a sine, or I can do a piecewise linear source. And so I can also do a small signal source. So I can add an AC amplitude here, like 1 volt, like I would do to make this an AC source in my netlist, right? And so just everything you're doing in LTSpice, you can think of it in the context of the netlisting you've been doing so far. Right? The syntax is oftentimes exactly the same as in your HSpice netlists, where you have the different, for piecewise linear, you'll have different times and voltages, things like that. And really, you'll see that all this is doing is making a netlist out of your drawing. Okay, so I can click OK, and this is now an AC source. I can also edit the values of resistors. I can add tolerances and power ratings as well. I can edit capacitors, add series resistance, things like that. Now, to connect things, you can go up to the toolbar and click this wire button. It's like a pencil, or you can hit W. Actually, sorry, F3. That's a different application. Hit F3 and you'll go into wire drawing mode. And then you can just basically click every point you want to make an angle. And then when you have wires that are connected, you should get a nice kind of blue square indicating that they are overlapping and connected. Don't forget to always place a reference. So you have a nice ground symbol up there that'll allow you to place a ground anywhere. And you'll always want this before you simulate, because otherwise things will not converge properly. You can move components around in kind of 2 ways. You can move them where it'll actually just take the component and it'll break all the connections and move it. Or you can drag it, which will try to keep the wiring intact, right? A lot of times that'll make something weird and messy like this, and so you might just want to move it and redraw the wires anyways, but you have multiple options. And all of these kind of commands, they are almost like a toggle. So once I've clicked that command on the toolbar, I'm in that mode, and everything I click will have that command applied to it until I hit escape. Okay. I think I covered sources and how to add those. And yeah, you can explore the libraries. Current is how you add a current source here. You have diodes. You have your basic PMOS here. This is a 3-terminal PMOS, right? So the source and the body are connected. And then you can get the 4-terminal version where the body is separate. Same for NMOS here. Okay. Oftentimes these are enough, but actually once you get into maybe your project, you'll want to simulate with real device models so that you can get the most accurate simulations. Okay. So that's how you add other components. And here you can right-click on that MOSFET and you can add, the length and width, the drain area and the source area. So these are kind of the parameters you would add in the same line as your MOSFET instantiation in your netlist, right? So you would add the length and the width afterwards. And so I guess for this next part, I'm going to go back to my my presentation because I don't have a simulation actually set up for you here. But basically, when you, let's go back and I'll just show you how to set up a simulation controller. So if you go to simulate and you click edit simulation command, you can then basically choose from the different simulation types that we're used to, DC, AC, transient, and you can either use the syntax guide here and type up the simulation controller command, or you can just type in the, so for the AC analysis, I can do number of points. I can do start frequency is 1 hertz, stop frequency is 1 megahertz, and I can do, you know, linear sweep, and it builds that simulation command for me. And this should look familiar, right? This is just a simulation command you would write in your netlist anyways. Click OK, and then you'll be able to drop it. It looks like a label, like a piece of text, but really this is going to be something that SPICE uses to control the simulation. You can also just add a SPICE directive. So say I want to do a dot include, right? I could do my, say I have my op amp model file in this folder. I could do dot include, and that's how I would include it, right? Any line that would go in your netlist that's not a component should be a SPICE directive. One thing that's really useful, and you could actually do this in HSPICE too, although I don't know we ever mentioned it, is you can add a line that says .op. Doesn't need any arguments. All it should say is .op. You can add this in your netlist, or you can add it like this. And what this will do is this will do a DC analysis in addition to whatever other analyses you have. So it'll do the AC analysis, but before that, it'll find the operating point. And in the output file, it will show you all of the different node voltages and currents and things like that. Okay. So this is where I'm going to go back to my presentation. If I can. Yeah, my computer doesn't want to let me do that in tablet mode. Oh, I think it's because it was full screen. Okay. So when you want to simulate, you'll click the run icon. There's a little guy running. Like I showed you, you can set up your simulation controller. If there are no errors, you should get a new window with a blank plot. What you'll do is you'll right click anywhere in that window and you'll get the option to add traces. Those traces will be kind of like the same form you saw in waveforms. It'll be like V and then parentheses in the node name for voltage, and it'll be I and then parentheses in the branch name for current, or like the component name usually. And so you can then choose to plot V of VO, and you can use math expressions like you would in waveforms. So you do V of VO divided by V of VI to get the gain, things like that. And one thing that's not necessarily intuitive, but you will double click on this name here. So at the top, you should see the name of your trace here. This is the current through R2. So here what we're simulating, if you're curious, is basically a resonant circuit. So something that looks almost like a bandpass filter. This is actually a model for a MEMS resonator, if you're wondering. But that basically has a resonant frequency at a certain point here, and then very low transmission at all other frequencies. And so, like I was saying, the name of the trace will be up top. If you want to add a cursor, you can double click that, and that'll add cursors that you can then, basically you can have two cursors and then see the delta between them. Okay, the last thing I want to say is that basically every SPICE circuit is represented by a netlist. What this is doing, like I said, is turning your drawing into a netlist anyways, your schematic into a netlist. And so you can actually go to view and look SPICE netlist in the LT SPICE schematic window, and it will show you basically the netlist that corresponds to your drawing. You can then edit that netlist if that's easier for you. And it's up to you whether you want to use LT SPICE or what you want to keep using HSPICE. Even if you want to use a different version of SPICE, at this point it's up to you. Not all of them are free, but that's why we gave you LT SPICE kind of guidelines, because it's free and most people can access it. but really it's whatever works best in your workflow. You might find as you get to the project, you want to write a script to help you iterate through some designs. Like, we saw just today that in lecture, iteration can be kind of tedious. And so if that's something you want to script, well, maybe you want to pipe the outputs of that script directly into a netlist, right? In that case, that might be way faster than reading the outputs of the script and going to your schematic and clicking around and changing the values one by one. And so that's where netlisting can be really important and powerful. And so that's why we wanted you to get some exposure to it. But in the end, we're not going to force you to use it anymore. If you never want to netlist again, that's okay, but you might be limited in some cases. And then, okay, let's see. Okay, that's all I have to say about LT-SPICE. Any questions about LT-SPICE? Okay, if there aren't any questions, then let's take a look at homework 7, problem 1. I'll probably spend more than just the next 2 minutes talking about this, so feel free to leave whenever you want. But this hopefully should give you some, basically a place to start when you're working on this assignment. So this is a problem that's actually kind of very similar to the derivation that Professor Nguyen did in lecture. I think it was lecture 16, I'm not sure. But what we have here is a top view and a cross-sectional view of a MOSFET. So this cross-sectional view should look kind of similar to what you've seen in the past, without some of the detail maybe you've seen in other figures. And then the top view, oh, what's the advantage of H-SPICE? I kind of just said it. So you can basically do, your net listing can give you kind of a better workflow if you're basically simulating designs. Like, for example, you can even netlist in more complicated circuit simulators. So there's one called ADS made by Keysight, or Agilent, formerly Agilent, now Keysight. And even ADS has netlists. And so I can basically run a script to create a design, and then I can automatically send that design and turn it into a netlist. Then I can use that script to send the run command right to my simulator, and then the simulator will create an output file, and then I use the same script to read the output file. So I run the script once, it creates the design, it simulates it, it reads the output, and then it'll plot the output for me. And so that's the advantage of H-SPICE. That's one advantage. H-SPICE, I think, is probably a little more features than LT-SPICE, in that LT-SPICE is free and H-SPICE is not. And there are slight differences in syntax. I forgot to mention this, but for example, if you're defining the threshold voltage in a model file, in LT-SPICE it uses VTH0, but in H-SPICE it uses VT0. So you got to be careful about that. Okay, so let's take a look at this problem. So the difference here between this problem and what you saw in lecture is that this W is a function of X. And so let's call this X in this direction and call that X equals 0 at the source. And so now we can basically walk through the same derivation, but substituting W of X for W. And so I'm just going to kind of work through this. So to get the current in the channel, we take the current at each point X and say that current will be the product of the charge per unit length, Q prime of X, times the velocity of electrons at that point, X. That velocity, let's see, that Q prime, the charge per unit length, is going to look like negative, because of their electron, CV, right? Q is equal to CV. And so C in this case is going to be the charge per unit, or sorry, the capacitance per unit length. So C prime, not C double prime, at each point X, times the voltage at each point X, which is going to be VG minus VS, VGS, minus VTH, minus the voltage at that point X in the channel. Okay? That's Q prime, where we have kind of the Q equals CV. And then the velocity is going to look like negative mu n, which is the mobility of the electrons, times the field in the X direction at point X. Okay, so that gives us the velocity. Now, to get the capacitance per unit length, we can take the capacitance per unit area and multiply it by the width. So that's what I'm going to do. I'm going to take the width, which remember is now a function of x, and multiply that by the capacitance per unit area, Cox double prime. I guess I could call that Cox up there as well. And then that's still going to be multiplied by VGS. Well, I'll replace VGS minus VTH with VOV minus V of x. All times. Let's get rid of both negative signs. Mu n. And actually what I will do is I will substitute for the electric field. I know that's going to be negative dV dx, where that, to be clear, this is the velocity. So the v with an x subscript is velocity, and all the other subsequent v's are going to be voltages. Yeah, I'll just keep that capital. And so the electric field by definition is negative v dv dx, where v is a function of x. And so I'll move that negative sign to the front. I'll take negative dv dx substituted for the electric field. So now we can start to actually rearrange. And so we want to get the current, but to integrate, or I should say to get the current, we'll need to integrate. And so I'm going to move the things that are a function of x kind of over to the left-hand side. I'm going to move my dx over to the left-hand side. I'm going to keep the negative sign here. Cox double prime, remember, it's just the permittivity of free space times the relative permittivity over the thickness of that gate oxide. And in this case, you probably want to just keep everything in the same units. So I like to put everything in meters, but you might want to put everything in centimeters. It's up to you. And then this is going to be VOV minus Vx times mu n dV. And so now we can integrate. So we want to look at dx as we go from 0 to L. And we can actually say that I of x is going to be negative I ds. So I'm going to say that I of x actually is constant throughout the channel. Otherwise, we would have some accumulation of charge. And so I of x, the way we've defined x, right, the current I of x is going to flow in this direction. But we know that I ds, the drain to source current, is going to flow in the opposite direction. And so I'm substituting negative IDS for I of x. And we'll see that'll cancel with a negative sign on the other side. And then for W of x, well, that's your job. What is W of x? Some function of x. And so we know it's going to be a linear function, right? Because W relates linearly to x, and there's going to be some kind of offset. And so it's going to be something like basically some mx plus b, right? So you have to find these. Be careful with units. And what you'll get is that you take the derivative, the integral of this IDS times 1 over W of x dx. And then on the other side, we're going to take our variable of integration to be the voltage, dV. So that voltage is going to go from 0 to VDS. And what we'll get is something that is quadratic, like we expect, because we have a linear function of V in our integral. Let's move the mu mobility out here. We get a linear function of V in our integral, and so we know the integral of that is going to be quadratic. Basically, you're going to have a V squared, right? So at this point, we can pull out the negative signs and cancel them. We can pull out the IDS. And basically, you can say that I'm going to have mu n. I'm going to rewrite that as Cox double prime, because you know now that those are the same thing. this part here, right? Cx double prime. And then we'll get that it's VOV, which is VGS minus VTH, times VDS minus 1/2 VDS squared over 2. Just say the total signal VDS. So that's after I integrate and plug in the bounds for the right-hand side, and then your job is to figure out what this is. It's going to be ln of something, right? Because I'm going to have something that looks like 1 over x. And I'm going to plug in 0 to L for my bounds there. And so you should end up with something that you get a number for, because we have a number for L, right? We have a value for that. And so you should get something that looks just like the drain to source equation, drain to source current equation, but with some modifier, because basically you're given values for W. And what you need to figure out is the effective width of W that's not constant. Are there any questions about this? Yeah.
Yeah, I have a question about this. So if V is also linearly changing from source to drain, is it fine if we wrote W as a function of V?
Yeah, you should probably be able to do it that way. I'm not sure off the top of my head exactly what that looked like, but yeah, you could probably write W as a function of V and keep it on the other side, and it would come out to the same thing.
Okay.
Yeah. Yeah, whatever works for you. Again, this is a physics problem that really requires you to understand what's going on. And so whatever helps you visualize this the best, please use that method. But this is just how one way to do it. And so hopefully this helps you. Feel free to come by office hours if you have more questions, but I think that's all I have for today. So thanks, everybody.